Hello. So today we will basically finish matrix norms, and our focus will be nuclear norm, which, as I said last time, is a summation of the singular values of the matrix. And we want to verify that this is a matrix norm. So remember, to be a matrix norm, basically the function applied to the matrix of the elements should give you a real valued non-negative quantity, okay, and it should be 0 if and only if A is the all zero matrix, and it should be homogeneous. So basically, if you apply it to the matrix multiplied by complex scalar, this should give you the magnitude of the scalar multiplied by the norm, okay. And then we should have a triangle inequality. Okay, so this means that if you have two matrices, and then basically the norm is subadditive, so the norm of the sum is less than the sum of the norms. And the same applies to multiplication. So if we have AB, take the norm, this should be less than the norm of A, the norm of B. Okay, so in this lecture, we'll focus on basically the challenging tasks of basically showing that indeed, if you define a function as the sum of the singular values, basically what you have is something that is subadditive and submultiplicative. So to show basically that we have the triangle inequality satisfied, what we will do is that we show that the sum of the singular values can be written in another way. It can be written as the solution to a maximization problem in which you maximize the magnitude of trace Q Hermitian A over Q. So Q is a matrix of the same dimension as A, and its maximum singular value is less than or equal to 1. And to show that actually these two quantities are the same, we will do it in the standard way. So we will show basically that this maximum is less than or equal to the sum of the singular values, and then we will show that this maximum is greater than or equal to the sum of the singular values, and so it is equal to. Okay, so let's start. So we have the maximum of this magnitude. Okay, so you have a magnitude of trace, and this gives you like basically this idea that perhaps the Newman trace inequality is involved, and it is. So basically we have here the magnitude of trace Q Hermitian A. So by the Newman trace inequality, this magnitude of a trace is upper bounded by a sum, the sum of the respective singular values of matrix Q and matrix A. Now matrix Q is chosen such that its L2 norm is, which is the maximum singular value, is less than or equal to 1. So this means that the singular values of Q are all less than or equal to 1. So we can upper bound this. So this is less than or equal to 1. So we can upper bound this by basically the sum of the singular values of A. And so Q like here disappeared, and the maximum over Q will basically be this sum. Okay, so these two lines, you are showing that the maximum of the magnitude of the trace is less than or equal to the sum of the singular values. So we need to show the other inequality. So let's start with the maximum again, the maximum of the magnitude of the trace. Now what we will do is the following. We will set Q equal to something. Okay, so there is, if there is a solution, let's assume that there is a solution to this optimization problem. There is a Q that will maximize this quantity. Okay, suppose that you don't know what it is. Okay, but so what you will do is that you will say, okay, definitely the maximum will be greater than if I just set Q to some strategically selected matrix. And so what we will do here is that we will say, okay, so the maximum over Q is greater than or equal to if we replace Q by some matrix, which is UAV Hermitian. Note that this matrix satisfies the constraints, because this matrix is M by N, and then if you use UAV Hermitian, you can basically think of a matrix living between these two guys that has 1 on the main diagonal and 0 here. So basically this thing is UA IRR VA Hermitian. So it's a matrix whose singular values are all equal to 1, which satisfies this, because here we want the maximum singular value to be less than or equal to 1, and this will, here we are just using that all the singular values are equal to 1. So what will happen if you do this? If you do this, of course, you get this inequality because this is the maximum. And now write A in terms of its reduced SVD. Okay, so Q Hermitian will be UA VA Hermitian. So this is Q Hermitian, and then A itself is sorry, we need to write Q Hermitian, not Q. So Q is UA VA Hermitian, so Q Hermitian will be VA UA Hermitian. Okay, and then A itself is UA, and then the matrix of the positive singular values, and VA Hermitian. So these two guys, because UA has orthonormal columns, then UA Hermitian UA is identity, and so you have VA SVA Hermitian. Now we know that the trace of so suppose that you have two matrices, one of them is K by L and the other is L by K. Then the trace of the product, you can basically swap the two matrices, you will get the same trace. So we can do this, we can simply move this to the other side. So this is equal to the trace of VA Hermitian VAS. Well, VA is like UA, it's a matrix with orthonormal columns. So VA Hermitian multiplied by VA is identity, and we are left with the trace of S. And the trace of S is the sum of the singular values. We no longer need the magnitude outside because the singular values are real valued and non-negative. So we prove that this maximum is less than or equal to the sum of the singular values. At the same time, this maximum is greater than or equal to the sum of the singular values. So in fact, this maximum is equal to the singular values. And this means that all the inequalities that we see here and there are all satisfied with equality because the maximum is equal to the sum of the singular values. So in fact, the Q matrix that we used here is actually the optimal solution to this optimization problem. Okay, and so this, we get the maximum here of the magnitude of the trace if you choose Q to be basically, to have the reduced SVD of A, but with the singular values of A replaced by ones. Okay. Okay. So while doing something like this, again, this is very useful to prove triangle inequalities. Okay. So now the triangle inequality becomes very straightforward. Now, what is the nuclear norm of the sum? So it's the maximum of this magnitude of trace involving the sum. And then you apply the triangle. So basically you separate two terms and you apply the triangle inequality, and then you apply the idea like in the previous lecture that the maximum of a sum is less than or equal to the sum of maxima, and then each one of those terms is the nuclear norm of matrices A and B respectively. So so basically this is one way of, again, if you find it difficult to prove the triangle inequality, one way you ask yourself is, can I actually represent my function as a maximization problem? Okay, and if you are able to do this, then these are the steps and you are done. So these are similar to what we did in the previous lecture regarding induced matrix norms, because they, but induced matrix norms, they are defined as a maximization problem. Here the main definition is a sum of singular values, but if you think hard enough, you come up with this equivalence between the sum of the singular values and this maximization. Okay, so triangle inequality is basically straightforward once you establish this equivalence. What about this function being submultiplicative? Okay, so this is a bit trickier. So the nuclear norm of A and B, okay, is the sum of the singular values. The problem is that like the singular value of a product of two matrices, it's not directly related to the singular values of each matrix, okay? So the best you can go for are bounds and so on. So now, you know, if you want to show that this thing is less than or equal to the nuclear norm of A and nuclear norm of B, okay? So what is required is to show that this quantity is less than or equal to summation, and then you take the singular values of A, singular values of B. Okay. So how can we establish something like this? You know, singular values are not like defined in like a nice way. And note that our, you know, here that our inequality involves, it's not just the maximum singular value. Basically, we take the maximum and then the next guy and then the next guy. It's a sum over all singular values. So our friend here is the Courant-Fisher representation of eigenvalues, which is a very nice theorem, and you'll find its proof in the notes on eigenanalysis of eigenvalues. Okay, so basically the idea here is to represent eigenvalues. You know, and singular values are are the square roots of the eigenvalues of the Hermitian of the matrix multiplied by the matrix itself. So basically, you represent eigenvalues as the solution to a minimax problem or a max-min problem. Okay, so let's start. Take sigma k of B. So that's the kth singular value of B. Again, in the notation in this course is that basically we have sigma 1 is the maximum, and then the largest, and then sigma 2 is the second largest, and so on. So sigma k is the kth largest singular value, and it is the square root of the kth largest eigenvalue of B Hermitian B, okay, which is a Hermitian matrix. So basically, the min-max representation of an eigenvalue tells you this. The kth eigenvalue of a Hermitian matrix can be obtained via solving this min-max problem. Okay, so you have basically a quadratic form. It has the Hermitian matrix here and a vectors, okay? And so what you do is the following. You choose a subspace. Okay, so B Hermitian B in our case here, I assume that B is n by L. So B Hermitian B is a square L by L matrix. So here we are talking mainly about the L dimensional complex space. So we choose a subspace in the L dimensional complex space. But not any subspace, its dimension is L minus k plus 1. Note that this k here is the same as the k there. So if k is 1, you should put a 1 here. If k is 2, you should put a 2 here. If k is 3, you should put a 3 here, and so on. So you choose a subspace with a particular dimension, specifically L minus k plus 1. In that subspace, what do? You solve this maximization problem. So you find the vector x with unity L2 norm, and this vector must be living in the subspace such that this quadratic form is maximized. Okay, so it's a min-max problem, which means that you do imagine like this. You do this for every possible subspace with dimension L minus k plus 1, and then you choose the minimum of the maxima. Okay, so for each subspace of dimension L minus k plus 1, you obtain the maximum value of x Hermitian B x for x that lives in the subspace and that has an L2 norm of unity. And then what you do is that you select the minimum. Okay, so you solve this for every subspace, okay, for every subspace possible with dimension L minus k plus 1. For each subspace, you get a number. Okay, you get a result for the maximization problem where you choose the minimum of them. So basically, this will be the kth largest eigenvalue of the Hermitian matrix that you are using here. So this is a very powerful characterization of the eigenvalues of a matrix. Okay, so now we can write down this inequality. So the kth largest singular value of B. Okay, so when you solve this problem, okay, there is an optimal subspace. So there is an optimal subspace, which is the subspace whose maximum is minimum. It's the subspace in which whenever you solve this problem, you get a value, and this value is the minimum over all possible subspaces with dimension L minus k plus 1. Okay. So over that subspace, what are you doing? You are maximizing with respect to x. You are maximizing. So sigma k of B, which is given by this expression, the min-max basically expression, is greater because it's over the optimal subspace you are maximizing. It's greater than or equal to basically this quantity itself, right? Because I mean, what the objective function here is just the L2 norm squared of Bx, and whatever you apply, this is the eigenvalue, and the singular value is just its positive square root. So the singular value means that you just, rather than using the L2 norm squared, which is this quadratic form, you just use the L2 norm itself. Since you are over a certain subspace, and here let's talk about the optimal subspace, the maximum, when you maximize, it means you get something that is greater than or equal to the L2 norm of B multiplied by x for every x that has a unity L2 norm and which lives in this optimal subspace, by definition, right? Because in each subspace, if you fix a subspace, you maximize. Okay, so if you choose the optimal subspace, okay, and in the derivation of the Courant-Fisher representation, actually you obtain actually what those subspaces are, but it's not relevant to us today. You can again read the notes and read the derivation to know what are actually the optimal subspaces. But for us today, I mean, again, it's like for the optimal subspace, you are solving a maximization problem. So the kth largest singular value is greater than or equal to this quantity itself, because over that subspace you are maximizing. So this is true for every x with unity L2 norm and x living in the optimal subspace. Okay. Now, this theorem here it has another version. Okay, so we'll apply the other version to the kth largest singular value of AB, A times B. So the other version tells you the following. If you want the kth largest singular value, again you can do it like in slow motion by relating basically the singular value to the square root of the eigenvalue of the Hermitian multiplied by this matrix. But again, we can just do it like above. But here, see the difference? In this formulation, what you do is the following. You basically choose a subspace with dimension k. So k here is k there. And now what you do is that over the subspace, you minimize this quantity. So you minimize the L2 norm of ABX for every basically subspace of dimension k, and then you choose the maximum of the minimum. Okay, so again, that's another formulation. And now, because over each subspace we are minimizing, so sigma k of AB is less than or equal to the L2 norm of ABX for every x in the optimal subspace, and that has a unity L2 norm. Again, why less than or equal to? Because here we are minimizing. Above we are maximizing. So see the difference between the two formulations, it's min and max are swapped and the dimension of the subspace is different. Here it's L minus K plus 1 and here it is K. Now, what is the issue now? Well, we want to relate the singular value of a product to the singular value of at least one of the two matrices, so that we show that this thing here is submultiplicative. So you apply this Courant-Fisher representation, the min-max form to sigma k of B, the max-min form to sigma k of A, B, and then what? The conclusions here, do not seem like related, but they are. Why? So when you solve the above optimization problem, you do it for subspaces with dimension L minus K plus 1. So the optimal subspace is one of those subspaces that you use here. And what is its dimension? L minus K plus 1. The problem that you solve here, you do it over subspaces with dimension K. And so S2, which is the optimal solution, has dimension K. Then what? What is the sum of the dimensions? Dimension S1 plus dimension S2 is L minus K plus 1 plus K. That's L plus 1. It's greater than the dimension of the embedding space. So if you have a space of dimension L and you have two subspaces in that space, and the sum of their dimensions is strictly larger than L, then there is a theorem in linear algebra that it must be the case that these two subspaces have a non-trivial intersection. Every subspace, by definition, contains the all-zero vector. This is from the definition of a subspace. The subspace of a vector space, it's like a vector space on its own, and so it must have an identity element for vectors. You must have something that if you add a vector to it, you get the vector back. So subspaces always, in our case here, always contain the all-zero vector in the L dimension space. So if you pick two subspaces, they must intersect in, or their intersection must contain at least one vector, which is the all-zero vector. The question is, do we have other elements in the intersection? So if the two subspaces have a sum of dimensions that exceeds the dimensionality of the space, then yes, the intersection is more than the all-zero vector. The intersection is non-trivial. And so now we can establish a chain of inequalities as follows. For every x in the intersection of S1 and S2, and the L2 norm of x is equal to 1. This point here is crucial, because if two subspaces, their intersection is just the all-zero vector, well, the all-zero vector has a norm of 0. It has a norm of 0. So you cannot have a vector with a norm that is equal to 1. Okay, so this point here, it may seem like, so what is the use of this in the proof? Without this point, you cannot make this argument. Basically, if the intersection is trivial, then the norm of the all-zero vector is just 0. But we are solving our optimization problems using vectors with unity L2 norm. So that's the reason we needed a non-trivial intersection, so that we have vectors other than the all-zero vector. So for every x living in the intersection of S1 and S2, and now we can say, yes, we can find the vector with unity L2 norm, right? Because if the intersection is non-trivial, it means that in the intersection, you can find a vector other than the non-zero vector. And this vector can be scaled to have a unity L2 norm. And remember, in any vector space, and hence in any subspace, if there is a vector, then you have all scalar multiples of that vector. So if there is a vector, you can the vector times a scalar must be also there in the subspace. Okay, so this is, again, it's more important than you may think. This will justify this statement. For every x in the intersection and the L2 norm of x is 1, yes, we know that basically we can find such an x. Sigma k of AB is less than this L2 norm. Because here we used the max-min formulation, and in the max-min formulation, if you fix a subspace, you minimize. So you get less than or equal to. So here we will have the L2 norm of AB multiplied by x. But the L2 norm of AB multiplied by x, as we did in the previous lecture, is less than or equal to the L2 norm of A, which is the maximum singular value of A, multiplied by the L2 norm of this vector, which is Bx. But from above, the L2 norm of Bx is less than or equal to the kth largest singular value of B. So this is less than or equal to that. Why? Because of this min-max problem. Once you fix a subspace here, and we fix it the optimal subspace, then basically you are solving a maximization problem. And so the singular value is greater than or equal to this L2 norm. And so we have a very nice inequality. Very nice in and of itself. We proved that despite the fact we cannot have an equality relating clearly the singular value of a product and the singular values of each matrix, we have inequalities, and this is one of them. The kth largest singular value of a product of two matrices is upper bounded by the product of sigma 1 of A, which is the maximum singular value of A, multiplied by the kth largest singular value of B. Okay, so again, this is like sort of a standalone result that is nice. And whenever you find, okay, so let's just write it. It's very nice on its own. Whenever you find yourself, you need to establish a relation between the eigenvalues or singular values that are not the maximum and minimum, are better kth largest. Most likely, you will have in your proof to use basically the min-max and max-min formulation. So here we obtain this inequality. Okay, the remaining steps are sort of straightforward. How can we go from there to our, to show that the sum of the singular values of the product is upper bounded by the product of the sums? So here is the definition of the nuclear norm. So you sum, so R is the rank of AB, and now we know that the kth largest singular value of the product can be upper bounded by the kth largest singular value of B multiplied by the maximum, the largest singular value of A, which is not a function of K, so you can take it outside. And now sigma A is less than or equal to the sum of the positive singular values of matrix A, and this sum of the singular values of B is less than or equal to the sum of all positive singular values of B. And each one of those sums is the respective nuclear norm. So indeed, we have the nuclear norm of a product is less than or equal to the product of nuclear norms. Okay, the nuclear norm, we verified that basically this nuclear norm is submultiplicative. The nuclear norm again appears now in many optimization problems in data analysis and signal processing. Involving the nuclear norm enhances sparsity. It leads to solutions, like if you are doing it for a matrix, it leads to solutions in which the matrix has few non-zero values. Okay, and this topic, I mean, we will encounter it in bits and pieces along the way. So, so now our, basically most useful matrix norms. So the L1 induced norm, remember this guy, L1 induced norm, you compute the L1 norm of each column in A, and then you take basically the largest L1 norm of a column. Infinity norm, you do the same, but you do it to rows. You compute the L1 norm of each row, and then you pick the largest. The L2 norm, that's the maximum singular value. Then there is the Frobenius norm, which is the square root of the sum of the squares of the singular values. And it is also more, we can easily say it to be the square root of the sum of the magnitude squares of the elements of the matrix, or we can write it also using the trace. It's the square root of trace A Hermitian A. And then we now have this nuclear norm, which is, so basically the Frobenius norm, you sum like this, sigma r squared, so you go all the way to the rank of A, but in the nuclear norm, you sum not the squares, you sum just the singular values itself. Okay, most likely, if you do something, you read a paper or a reference or anything, you will encounter one of those norms. Of course, there are so many norms. Anything that satisfies the four properties will be a valid matrix norm, and definitely it will find some application here or there. Any question? Okay, so let's go to the next chapter on projectors. So projectors, basically, the story can start like this. Suppose that you have two subspaces in the n-dimensional space. These two subspaces, they intersect only in the all-zero vector, and we can write, I mean, what is the meaning of something like this when I write that the n-dimensional complex space is equal to S1 plus S2? This means that basically any vector in the n-dimensional complex space can be written as the sum of two vectors. Actually, it can be written as the unique sum. Okay, it's, you can show that this is unique. Again, like these ideas, like you studied in a first course on linear algebra. So you study this thing called direct sums. Okay, if you want to review it. And it means that, again, there are two subspaces. Their intersection is just the all-zero vector, so that's a trivial intersection. And, basically, together they give you the space in the sense that any arbitrary vector in the space can be written as x1 plus x2. So you take any x, you can write it uniquely as x1 plus x2, where x1 lives in S1 and x2 lives in x2. Note that S1 and S2, do not need to be orthogonal. We will later talk about them being orthogonal, but for now, they do not need to be orthogonal. Okay, so let's give you an example. So in R2, the two-dimensional Euclidean plane, for example, you can take S1 to be the span of the vector 1, 0. And you can take S2 to be the span of the vector 1, 1. So any vector in the n-dimensional space can be expressed uniquely in terms of multiples of these two vectors, right? So these two vectors, right, they are like, they basically satisfy everything that we have here, but they are not orthogonal, right? They are not orthogonal. If you choose S2 to be 0, 1, the span of 0, 1, then we have orthogonality. Okay, so for now it's general, and we do not insist on orthogonality. Orthogonality means that each vector in S2 is orthogonal to each vector in S1. We don't have this for now. Okay, definition. We will define matrix P as the projector onto S1 along S2. The projector onto S1 along S2 if B satisfies the following. B must actually satisfy two things. If you take a vector living in S1, B multiplied by that vector must give you the vector itself. And if you multiply B by any vector from S2, you must get the old zero vector. Okay? So, if the vector is in S1, Bx1 is x1. If x2 is in S2, then Bx2 is equal to 0. If you have a matrix satisfying this, then we say that the matrix is a projector onto S1 along S2. If you apply the projector to a vector x, so it's called a projector or projection matrix. If we apply the projector or projection matrix to an arbitrary vector x, so we said that an arbitrary vector x can be written as the sum of the unique sum of two vectors, one in S1 and one in S2. So if you multiply b by x, you get bx1, that's x1, plus bx2, that's 0, and so you get x1. So for an arbitrary vector, b times x will give you what? Will give you the component of the vector living in S1. Okay. So, we need to understand B. We need to understand matrix B. Before scrolling down, so for example, from these two equations, you may think that B has eigenvalues that are 0 or 1, right? This is an eigenequation, right? You are saying that Bx1 is equal to 1x1. And then from here, it's like Bx2 is 0x2. So in fact, we will show that a projection matrix, its eigenvalues are just zeros and ones. So you may get this impression from here, and it's true. Okay, let's basically justify this and basically derive, what are the general properties of matrix B? So let's suppose that the dimension of S1 is equal to R, and suppose that we have an n by n matrix like this. So the first R columns in matrix big Q, they are a basis for S1. So those R vectors are basis for S1, and the remaining vectors in Q from QR plus 1 to Qn, those are a basis for S2. Okay, so you have two subspaces, okay, that you know the dimension. So if the dimension of S1 is R, the meaning of the dimension is exactly this. If the dimension of S1 is R, it means that there are linearly independent vectors such that any vector in S1 can be written as a linear combination of those R vectors. And S2 will have dimension n minus R, and we will need those vectors to basically express any vector in S2. Now, Q is invertible. Matrix Q is invertible. Note that the first R vectors are a basis. So by definition, they are linearly independent. The vectors from QR plus 1 to Qn are another basis. So by definition, they are linearly independent. Can it be the case? Can it be the case that one of those vectors can be written as a linear combination of the other vectors? So can QR plus 1 equal to 1? No, exactly, no. If you do it, if you can do so, then S1 and S2, their intersection is non-trivial. Their intersection is non-trivial because, you know, remember that the basis vectors are never the all zero vector. Okay? So basically, if one of those guys can be written as a linear combination of the others, and it's a non-zero vector, then actually one of those vectors is living in S1, or vice versa. If one of those vectors from Q1 to QR can be written as a combination of QR R plus 1 to Qn, then it's living in S2. But remember, from the very beginning, we are saying that these two subspaces, their intersection is only the O0 vector. So we cannot express any one of those guys in terms of those, and vice versa. So it means that all those Q vectors are linearly independent. Matrix Q is invertible. Okay, multiply P by Q. So you multiply P by each column. Now Q1 up to QR are living in S1. Our rule dictates that P multiplied by those vectors will give the vectors themselves. Those other vectors are living in S2. By design, B will give you 0, the zero vectors, the all zero vectors. So PQ gives you basically this. And this matrix here, in which basically you have those columns are all zeros, and then the first columns are Q1 to QR, can be written as matrix Q, and then this matrix, which are the all zero matrix, but you have an R by R identity here. Because Q is invertible, you can multiply both sides by Q inverse from the right, and so now Q is equal to Q multiplied by this matrix multiplied by Q to the minus 1. You can now make a big conclusion. What does it mean that you can take a matrix, write it as an invertible matrix, a diagonal matrix, and then the inverse of the invertible matrix? It's eigendecomposition. That's exactly eigendecomposition. So it means that matrix B is diagonalizable. Its eigenvectors, its eigenvectors are here, and actually its eigenvalues are living in this matrix. There are R eigenvalues that are equal to 1, and N minus R eigenvalues that are equal to 0. Also, if you take matrix B and multiply it by itself, okay, then when you multiply this by itself, Q inverse Q is identity, and if you multiply these two matrices, you get the same matrix again. So actually P squared is equal to B. So matrix B, is idempotent. It is one of those matrices in which if you square the matrix, you get the matrix itself. Okay, so here is the list of our conclusions. So B, again, what is B? Projector or projection matrix onto S1 along S2. S1 and S2 are not arbitrary subspaces. They need to satisfy that S1 intersection S2 is the all zero vector, and that any vector in the n-dimensional space can be written as a vector from S1 plus a vector in S2. Now this matrix, now we know some of its properties. It is idempotent, it is diagonalizable, its eigenvalues are 0 or 1. The geometric multiplicity of the eigenvalue 1 is equal to the algebraic multiplicity is equal to R. And R, remember what is R? R is the dimension of S1. Rank of B is equal to R, and the dimension of the null space of B is n minus R, right? So basically those vectors from QR plus 1 to Qn, those are a basis for the null space of B. Those are the vectors. If you multiply P by them, then you get the all zero vector. Okay. Now, how is S1 and S2 related to the column space of P and to the null space of B? Let's see. You know, it seems like S1 is the column space of B and S2 is the null space of B. That's true. I mean, if X is in S1, by definition, Bx is equal to X. And if you see something like this, it means that there exists a vector such that B times the vector gives you X. So X is in the range or column space of B. So you start with a vector in S1, you end up with a vector in the range or the column space of P. So it means that S1 is a subset of the range of B. But these two guys, they have the same dimension, so they must be the same. Okay, so the range of B is indeed S1. Similarly, if X is in S2, Bx is 0, so X is in the null space, so S2 is a subset of the null space, but again they have the same dimension, and so they are the same. So basically the projector onto, so basically, so P is the projector onto S1 along S2. So basically S1 is range of B, or let's put it like, you will discover that range of B is S1 and the null space of B is S2. And this is sort of by design. Remember the very beginning, we wanted this property that if you choose a vector in S1, you multiply P by that vector, you get the vector itself. If you choose a vector in S2, you multiply B by the vector, you get the all zero vector. So it's like by design, all these properties will follow once you force these properties. Now, it turns out that, you know, suppose that you want to switch the role of S1 and S2. So suppose that you want a matrix that if you multiply it from a vector in S2, it gives you the vector, and if you multiply it by a vector in S1, it gives you the all zero vector. So you can discover basically that this matrix is nothing but In, so the identity of n, you know, of size n by n minus p. So this will be the projector onto S2 along S1, which means that this thing here times bx is equal to x if x is in S2, and you can verify that easily, and n minus p if is times x is 0 n by 1 if x is S1. Okay, so if you want to switch the roles of S1 and S2, I mean, just use identity minus p, and you can always verify these properties that identity minus p is idempotent, it's diagonalizable, its eigenvalues are just 0 or 1, but now the algebraic multiplicity of 1 is the same as the geometric multiplicity, is equal to n minus r. Okay. So in fact, you can like show something that P is a projector if and only if I minus P is a projector. And these two projectors, again, they just switch the roles of S1 and S2. So a projector is idempotent. In fact, the converse is true, and hence basically projector. So P is a projector, even only if it is idempotent. Okay, so before proceeding, do you have any question? Okay, so suppose that you start with a matrix that is idempotent. Okay, so no S1, no S2. We don't have this business. But let's see that this matrix will basically do projection as defined on the previous page. So suppose that you have a matrix that is, now our starting point is something completely different. It's just a matrix that satisfies that A squared is equal to A. Now, for this matrix, the null space of A is the range of I minus A. Let's prove this. So we want to prove that these two sets are the same. So we will use the technique that we will show that basically that NA is a subset of the range of I minus A, and that NA also includes or contains R of I minus A, and hence they are equal. Pick a vector X in the null space of A. So AX is equal to 0. Multiply both sides by minus, and so we have minus AX is the all 0 vector. Okay? Now add X to both sides. If you add X to both sides, you have X minus AX, which can be written as I minus A multiplied by X equal X. So now vector X here can be written as the matrix I minus A multiplied by some vector, which happens here just to be X itself, not a problem. Our conclusion is the same, that X lives in the column space of this matrix. So you start with a vector here, it must be there. So the null space of A is a subset of the range of I minus A. Now what if X is in the range of I minus A? Then there is a vector W such that I minus AW is equal to X. Now multiply both sides from the left by matrix A. So here we will have AX, and A times I is A times A is A squared. But the matrix is idempotent, which means that A squared is equal to A. So we have here A minus A, which is the all 0 matrix. So basically AX is equal to the all 0 vector. So X must be living in the null space. So you start with a vector in the range of I minus A, you end up with a vector in the null space. So we have this. And together, these two means that the null space of an idempotent matrix is exactly the range of I minus the matrix. Now let's verify another property, that the range of A and the null space of A are basically, their intersection is equal to 0. I mean, where are we headed? I mean, what are we doing here? Okay, so we are trying to show that R of A, where A is an idempotent matrix, and N of A qualify as S1 and S2 on the previous page. Okay, so basically remember S1 and S2, their intersection is just the all 0 vector, and also any vector in the space can be written as a linear, as a sum of two vectors, one in S1 and one in S2. So we want to show that actually S1 and S2 can be played by R of A and the null space of A. How can we show that the intersection is the all 0 vector? Well, pick an arbitrary vector in the intersection, If it's in the intersection, then it is in the null space of A. Then AX is equal to 0. And it's also in the range. So there is a vector y such that AY is equal to X. Take this equation, multiply from the left by A, then A squared y is equal to AX. A squared y is equal to AX. But what is A squared y? A is idempotent. So A squared y is equal to AY, which is equal to X. And AX itself is equal to 0 because X also lives in the null space of A. Then we get the equation that X is the all-zero vector. Again, suppose that you don't know about this intersection. Perhaps it's the all-zero vector and other vectors. Take a vector X in the intersection. It is in the null space, so AX is 0. It is in the range, so there is y such that AY is equal to X. Multiply this equation from the left by A. Then A squared y is equal to AX. AX is 0. A squared y is equal to AY because A is idempotent. And AY is equal to X. So X is always equal to 0. So the vector in, the only vector in the intersection is the all-zero vector. Can we take an arbitrary vector in the n-dimensional space and write it as a vector in the range of A and a vector in the null space of A? Yes. Take W, write it as AW, but we have a W here. Okay, so if you put an AW, subtract an AW, and then add a W. Okay, so this is straightforward. W is AW plus W minus AW. Now take W here as a common factor to the right, and so W is equal to AW plus I minus AW. So we take an arbitrary vector. What is AW? AW is a vector in the span of the columns of A. It's a vector in the range or column space of A. What is I minus AW? It's a vector in the range or column space of I minus A. But the first thing we did here is to show that the null space of an idempotent matrix is exactly like the range of I minus the matrix. So basically this vector is in the null space because the null space is the range of I minus A. Okay? So the range of A and the null space of A, where A is an idempotent matrix, it's they are like S1 and S2 on the previous page. They are candidates basically for constructing a projector. And the projector will be A itself. Okay? So let's basically check that if you take matrix A and take a vector in the range of A, so it means that there is a y such that AY is equal to X. Multiply both sides by A from the left, then A squared is equal to AX, but A squared is equal to A, so A squared y is equal to AY, and AY is equal to X. So AX is X, which means that any vector X living in the range of A, if you multiply A by the vector, you get the vector back. And if X is in the null space of A, definitely, if you take A times X by definition, you get the all-zero vector. So an idempotent matrix, okay, so A, which is, this is crucial, which is idempotent, that is to say, A squared is equal to A, is a projector onto R of A, the range or the column space of A, along the null space of A. Any idempotent matrix is a projector, and from the previous page, any projector, you can see that from its definition, you can show that it is idempotent. So idempotent if and only if a projector. Okay, so these two classes of matrices are the same. Any question? Okay. Now, of course, the trivial projection matrix is the all zero matrix. So basically, the rank is 0. All eigenvalues are equal to 0. So let's exclude it. Suppose that B is a non-trivial projector. It is a projector with at least one eigenvalue of unity. Then what is a matrix norm of a projection matrix? The projection matrix is idempotent. So it is equal to itself squared. So it is equal to the product of its, of P by P. And then a matrix norm is submultiplicative. And if P is a non-trivial projection matrix, which means that it is not the all zero matrix, then its norm is not equal to 0. So you can divide both sides by the norm of B, and you get this inequality that a projector satisfies that the norm of the projector is greater than or equal to 1. So for any matrix norm, the projector for any matrix norm applied to a projector, you get something that is greater than or equal to 1 if you exclude basically the trivial projector, which is the all zero square matrix. Okay. Now let's go to orthogonal projection. Okay, so orthogonal projection, same story as above, but with an additional thing, that the two subspaces that we talk about are orthogonal, which means that if you take a vector, okay, so we take a vector, so for every x in S1, for every y in S2, the inner product x Hermitian y is exactly equal to 0. So here we insist also on orthogonality. So, which means that it's not just that we want the intersection between the range and the null space to be just the all zero vector. We want each vector in the range of B to be orthogonal to every vector in the null space of B. Okay. So for projectors that are not trivial, there are three mathematical statements that are all equivalent, and they are equivalent to the definition of an orthogonal projection. Okay. So how do we identify that our projection is orthogonal? Well, the first property is that the L2 norm of the matrix is exactly equal to 1. Is exactly equal to 1. Okay, generally the L2 norm, which is the maximum singular value of P, is greater than or equal to 1. So now if we focus on the L2 norm, we should get it 1 for orthogonal projection. Number 2, that basically this is sort of from the name that you want the range of B to be perpendicular to the null space of B. Number 3, which is very nice, is that your matrix is Hermitian. So if you have a projection matrix, okay, how can you identify a projection matrix? Say that it is idempotent. So someone tells you, oh, this matrix is a projection matrix. How can you verify this? The most simple thing, take the matrix, multiply by itself. If you get the matrix back, then it is a projection matrix. Now, how can we verify that it is an orthogonal projection matrix? Well, if it is idempotent and also Hermitian, then it is an orthogonal projection matrix. So how can we show that all these things are actually mathematically equivalent in the sense that every statement here implies the other? So we want to show that I implies double I, and double I implies I, and I implies triple I, and so on and so forth. So we will basically prove, so the idea is that we will prove that I implies double I, and that double I implies triple I, and that triple I implies I. And so we will basically show equivalence, which means that these statements are basically, you have implication in both directions. Okay, so let's focus first on showing that if you have a projector, a non-trivial projector, and its L2 norm is exactly equal to 1, then yes, the range of the projector is perpendicular, is orthogonal to its null space. Pick a vector in the range, pick a vector in the null space, and those two vectors are not the all zero vector, because trivially the all zero vector is perpendicular to any vector in the space, right? So we will focus on two vectors that are not the all zero vector. One of them is in the range and one of them is in the null space, and our objective is to show that if this is true, if the L2 norm of matrix P is unity, then actually vector x and vector y are perpendicular. Okay, how can we show something like this? So here is a way to write down vector x. It's similar to what I did on the previous page. So you take x, you say, okay, what is x? I will write x as y Hermitian. Okay, so that's a matrix, an n by n matrix, and I will just scale it by the L2 norm squared of y, x multiplied by x. But definitely this is not equal to x, so we need to subtract it. And we should have an x here. Then we combine these two terms by taking x as a common factor to the right. Okay, so we can write x as this matrix multiplied by x plus I minus this matrix multiplied by x. Okay, and let's call this guy R. So this second component R. Basically, these two components of x are orthogonal. Let's check. So what will happen if I take this component here, take its Hermitian, and multiply it by R, which is this I minus this quantity multiplied by x? Okay, so basically you will find that once you take the Hermitian of this quantity, that basically you will get, I mean, if you take Hermitian, you will get x Hermitian followed by y Hermitian. Now, if y Hermitian is multiplied here, y Hermitian by I gives you y Hermitian. Y Hermitian multiplied by, so this is, there is a scalar here which is 1 over y Hermitian y. So if you multiply this thing by y Hermitian, so basically this is exactly the same scalar, and so they go, and you are left with y Hermitian. So inside the bracket, if you take the outside y Hermitian and multiply it inside, you get y Hermitian minus y Hermitian, and so that's a 0. So basically these two components are orthogonal. Why did I verify this? Because now I want to take the L2 norm squared of vector x. So we know that if you have a vector x and it is equal to alpha plus beta, then the L2 norm squared of vector x is so basically it's alpha plus beta Hermitian multiplied by alpha plus beta. So it is the L2 norm of vector alpha squared plus the L2 norm of vector beta squared, right? But then you have cross terms, plus alpha Hermitian beta plus beta Hermitian alpha. So if the two components alpha are beta and orthogonal, we don't have these cross terms. Okay, so basically I did this first step to tell you, well, if now you compute the L2 norm squared of vector x, you just have the L2 norm squared of this guy and the L2 norm squared of R itself, which is this guy. Okay, so I will take the L2 norm squared, which is given by this plus that. Again, there are cross terms, and the cross terms are 0 because you can verify they are actually orthogonal to one another. And so the L2 norm squared of vector x can be written as the inner product of y as the magnitude squared of the inner product of y and x divided by the L2 norm squared of y plus the magnitude, the L2 norm squared of vector r. Okay, remember, vector x is chosen from the range of P. So Px is equal to x. Okay, so now we have x is equal to y Hermitian over y Hermitian y. That's just a scalar x plus r. Now multiply both sides by p, so px is, so you apply p. Now what happens here? You know, basically this quantity can be written as such. You can take y Hermitian x as a scalar divided by y Hermitian y as a scalar, and then you apply p to vector y plus pr. But y is chosen from the null space of p. So this is 0, and px is equal to br, and bx is equal to x itself because x is in the range of p, okay, the projector p. Okay, so let's basically use this. So we have this expression that the L2 norm squared of x. Okay, so x is equal to bx, and bx is equal to pr. So I can basically rewrite this equality as the L2 norm squared of PR is equal to this term plus this term. Okay. Now this is the L2 norm squared P times R. So it is upper bounded by the it's upper bounded by the L2 norm of P. Okay, so this is the matrix L2 norm. So it's upper bounded by P multiplied by upper bounded by the L2 norm squared of B multiplied by the L2 norm squared of R. Okay, and so it means that again, so this quantity is equal to that quantity, and that quantity is upper bounded by this product. Now we will use the given. Remember, we are doing this direction of proof in which we show that if this is true, then this, if I is true, then double I is also true. So it's given to us that the L2 norm of B is equal to 1, and so this guy is 1, and so now we have this inequality. We have the inequality that squared over y2 squared plus is less than or equal to. Now this guy is 1. And those can be cancelled. And so now we have that this magnitude square is less than or equal to 0. But the magnitude square is a non-negative quantity. So if it's less than or equal to 0, then it is equal to 0. Then y Hermitian x is equal to 0. So we proved that if the L2 norm of matrix P is equal to 1, you can show that if you pick a vector from the range of B, a vector from the null space of B, then these two vectors will be orthogonal. So the range of B and the null space of B are orthogonal. They are not just intersecting trivially. In fact, they are orthogonal in the sense that the inner product of any two vectors chosen from here and there will give you 0. Now let's prove basically that if you have the range of B orthogonal to the null space of B, then actually the matrix is Hermitian. Okay, so the range and the null space are perpendicular to one another. So the range and null space are perpendicular to one another. And previously, we have shown that basically any vector in the space, again, the range of B and the null space of B are, S1 and S2. Any vector in the space can be written as uniquely as a vector in range of B and a vector in the null space of B. They are orthogonal. So basically, the null space is the orthogonal complement of the range of B. Why? Because the null space is perpendicular to the range, and together they give you the n-dimensional space. So the null space of B is the orthogonal complement of the range of B. So basically it's the set of all vectors that are orthogonal to the range of B. Okay, so basically what is this set? So this is the set of the vectors in the n-dimensional space such that basically they are orthogonal to the columns of B. Okay, so if you take any column of B, so basically the column J Hermitian times Z, okay, is equal to 0 for every J, for every column in the matrix. That's the orthogonal complement, okay? And you note the following, that basically by definition of the orthogonal complement, okay, the orthogonal complement of the range is the null space of B Hermitian, right? Because if you write down, if you ask yourself what are the vectors such that, I mean, so let's write, what is this thing? Null space of a matrix, it means what? So these are vector W, okay, such that B Hermitian W is equal to 0 n by 1. And if B Hermitian W is equal to 0 n by 1, I mean, what does it mean? It means that B column 1 Hermitian W is 0, B column 2 Hermitian W is 0, and so on and so forth. Okay, and so basically the range, the complement of the range of B is equal to the null space of B Hermitian. Okay, so to emphasize, basically the relationship between these two guys is always there. Okay, so basically that the range, the orthogonal complement to the range is the null space of B Hermitian. What is new to us now is this extra assumption. We are already assuming that the range itself is orthogonal to the null space of B, and so the null space is the orthogonal complement to the range. Okay. Take a general vector Y living in the n-dimensional space. What is I minus P times Y? I minus P times Y basically is a linear combination of the columns of I minus P. You know, you take a matrix multiplied by a vector, you get a vector living in the column space of the matrix. So basically I minus P times Y is a vector living in the range of I minus P. But remember, P is an idempotent matrix. And previously we shown that for an idempotent matrix, its null space is exactly the same as the range of identity minus the matrix. So the range of I minus P is the null space of B. It is the null space of B. But in our particular case here, the null space of B is equal to the null space of B Hermitian. Okay? So this vector here lives in the null space of B. Okay, so basically I n minus Py, it belongs to the null space of B Hermitian. Which means that if you take B Hermitian and multiply it by this vector, you will get to the O0 vector. So B Hermitian multiplied by this vector here, you get the O0 vector. And so it means that P Hermitian minus B Hermitian P all multiplied by Y is equal to 0. The O0 vector, 0 n times 1. This is true. Do we have any constraints regarding Y? No, it's a general vector. So you can choose Y to be the vector E1, the vector with ones and then with a 1 followed by zeros. You can choose Y to be 0, 1, zeros, and so on. And so basically, because Y is general, basically this matrix multiplied by identity is equal to the O0 n by n matrix. And so this matrix here is equal to the O0 matrix. And so B Hermitian is equal to B Hermitian B. Now take the Hermitian of both sides. B Hermitian Hermitian is P itself, and B Hermitian B all Hermitian is B Hermitian B. So what do we conclude from here? That B Hermitian is B Hermitian B, and that B itself is B Hermitian B. Then those three guys are the same, right? Then B is indeed equal to B Hermitian is equal to B Hermitian B, which means that B is a Hermitian matrix. So if I give you an idempotent matrix and a projector, and I tell you that we know that the column space of that projector is orthogonal to its null space, it must be the case that the projector or the projection matrix is Hermitian. Now, if the matrix is Hermitian, we are guaranteed to get the L2 norm equal to 1. And now this is a one-liner. So basically, the L2 norm is the maximum singular value, and the maximum singular value is the square root of the maximum eigenvalue of B Hermitian B. Okay, and but because B is Hermitian, then B Hermitian is equal to P. If B Hermitian is equal to B, then this is equal to B squared. This is equal to B squared, and B squared is equal to B because any projector is idempotent, and so that lambda 1 of B squared is lambda 1 of B because B squared is equal to B. And so now a statement about the singular value of P is now converted to a statement about an eigenvalue of B. And we know that B is a projector, it's idempotent, and its eigenvalues are just zeros and ones. And so if it's not the all zero matrix, then the maximum eigenvalue of B is 1. And so basically we know that the L2 norm of B is exactly equal to 1. So now we have established that basically these three statements are equivalent. Okay, so each one of them implies the other. Someone tells you that you have a projection matrix, you know that the L2 norm or the maximum singular value is 1, you know that the range of B is orthogonal to the null space of B, you know that P is Hermitian. Okay, so again, projector, if and only if idempotent, and orthogonal projector, if and only if idempotent and Hermitian. Keep this in mind, very important. Whenever you deal with a projection matrix, keep this in mind. Generally, projector if and only if idempotent. If you want the special case of orthogonal projectors, then you need also the matrix to be Hermitian. Any question? In many cases, we want to project onto the column space of a matrix. To project orthogonally, okay? So in many applications, we want the orthogonal projection of, the orthogonal projection onto the range of A, the column space of A, along the orthogonal complement of the range of A, which is the null space of A Hermitian. Okay? So it turns out that give me a matrix A, a general matrix A, and if you want to orthogonally project onto the range of A, which means that you project onto R of A along the orthogonal complement of R of A, then your projector, you can verify this, is simply given by UA Hermitian, where UA is what you obtain from the reduced SVD of the matrix. Okay, so you can verify it easily. So the projection, if you want basically this matrix, it is B equal UA Hermitian. And this matrix can be written in other forms that are useful, So So suppose that you take UA Hermitian and you insert S. You know so again, this is just the reduced SVD, and so S is the I, R by R matrix of strictly positive singular values. So UAS VA Hermitian VAS inverse. So VA Hermitian VA is identity, and S by S inverse is identity. So basically, you can just insert those guys. And what is the purpose? Now, if you insert those guys, these three matrices are the Moore-Penrose pseudo-inverse. And those guys are the matrix itself. So again, in some application, it may be useful to write down the orthogonal projector onto the range of a matrix as the matrix multiplied by its Moore-Penrose pseudo-inverse. You can also write the projector in another form, which you will prove in homework 2, which is this form. So you can basically insert here A Hermitian A, the pseudo-inverse of A Hermitian A. And if A Hermitian A is actually an invertible matrix, you can replace the pseudo-inverse by the actual inverse. And so if the columns of A are linearly independent, you can write down the projector in this form, which is very useful. And for those of you who are taking the wireless course with me, basically this is what we will use for orthogonal projection. Okay, so you can write down the orthogonal projector again as UA Hermitian, or as A multiplied by the pseudo-inverse, or as A multiplied by the pseudo-inverse, A multiplied by A Hermitian, and between them the pseudo-inverse of A Hermitian A, or as A, A and A Hermitian on one side, and between them the inverse of A Hermitian A. Of course, if I write the inverse, I mean that it exists, and basically this requires that the columns of A are linearly independent. Okay, so your matrix A can be a vector, actually, a column vector. So if it's a column vector, what is basically this expression? If it's a column vector, then this is a scalar, right? So if you have A Hermitian A inverse, A Hermitian, and A is m by 1, then this is 1 by m, then this is 1 by 1, so it's a scalar, and I can write down something like this. So if you want to project onto the range of a matrix, which is actually just a column vector, then the projector has this nice formula. It's the outer product of the vector with itself normalized by the L2 norm squared of the vector.